And let's go to the last talk of the session. So that's Szymon Nakoneczny. I hope I pronounced that. I know with a name like Henry Joy McCracken, sometimes. So go ahead, please, and I'll make a sound at -5.
Yes, thank you very much. So my name is Szymon Nakoneczny, but it's a hard Polish name and surname, so no problem.
Sorry, we're seeing the presenter screen. We're not seeing
Yep.
So you need to invert your presenter screen and the other one. Are you in Keynote?
Okay.
Yeah.
Should be fine right now.
That's great. Yeah. Please go ahead.
Okay, thank you very much. So I'm based in Warsaw, Poland, and today I would like to show you my work I've done in kilodegree survey on photometric selection and redshifts for quasars. The work was published in two papers, the second one at the beginning of this year. So the structure of my presentation is very typical, but as it is a very machine learning related conference, I would like to stress 3 points, which are in my mind like main points to make a good machine learning application in any kind of in any application, but also especially in astrophysics. So the first point, very important point to my mind, is doing proper data research, visualization, and understanding of your data. Is why I think people call machine learning models black boxes, because they don't understand the data really well that the models work on, because the models are derived from data and mostly do what the data tells them to do. The other part is the validation during the training of the model, which has to be hard enough, might be involve already some physical ways to it, and the final output is the final thing is the testing of the final results, which should be physically driven in astrophysics. So I will show it how I do it in my work. So just one slide of introduction on the problem. In kilodegree survey is a broadband survey which is designed for mostly for weak lensing. The problem with detecting quasars is that they are very similar to stars. On this image on the left, you can see a quasar in the middle and the star over here. They are very similar. They can be separated in the color space, and most importantly, machine learning helps a lot with that. So this is the data. We have about 100 millions of objects, from which I take objects with 9-band detection, which leaves about 50 millions of objects, limited at R lower than 25. And I have the UGRI bands from kilodegree survey and also from partner Viking survey, the new infrared bands, which I use to create colors and ratios of the magnitudes, and it gives me a feature space together with a so-called stellarity index. So it's a classifier which tells whether object is point-like or not, quasars also being point-like objects mostly. And this is on the left, this t-SNE visualization, so two abstract dimensions made of the whole feature space. And on the left hand side is the all data in kilodegree survey. On the right side is the training data, which comes from cross-match with SDSS. And this already shows the problem which we have with extrapolation in feature space. We either have to cut the data so that the inference data matches the training data, and we have to be careful about the extrapolation. This visualization shows very interesting thing, because in the training data you can see quasars and stars separated from each other very nicely, but in the inference, so-called inference data, when we want to do the classification, these two groups are let's say touch each other. We don't know where is the proper decision boundary between quasars and stars in this data. So this visualization already shows us what is the problem that we have to solve, and possible limit of machine learning application. So what we do is we create several different so-called inference subsets. So we define a safe subset which is limited to the same magnitude as the SDSS. There's extrapolation subset which goes to fainter magnitudes, and there's also unsafe subset, and these are the objects for which the point classifier doesn't work. So this is basically, in the training we don't have such objects, as the training is brighter. In the inference we do, and we cannot expect the model to work on values of about 0.5, which basically this classifier then tells that it doesn't work, and the model will not understand such new values. So this would be a very random feature for the model. And this is the visualization of those inference subsets. So again, on the right is the training data, and left is whole data split into the inference subsets. So you can see that they progress with the magnitude, and basically the further we go with them, the less sure we are about the results of our model. And we can see also here in this especially most important part of where we divide stars from quasars, that the first extrapolation set is far from each other, but when we go to magnitudes fainter than 23, it's this most problematic part that we may be most unsure of. So we also define a testing set which specifically addresses this problem of extrapolation, because we want to have hard enough validation method when we are choosing the model, when we are choosing the parameters of the model. So we basically create two testing subsets. One is the faintest objects from the training data, and another one is randomized subset coming from the rest of the data. So basically we take 10% of the faintest object, and this results at the cut on error magnitude about 21.3. So now what are the results of this approach? This is a very important comparison. These are the training histories of the XGBoost model. On the left, you have the classification for the class versus quasar versus star versus galaxy. Then this is the redshift for quasars, and this is on the right hand side redshift for galaxies. Now what we can see is that with classification, the random test, you can also pay attention that the two lines have different values. The errors on the random set are always very much lower than on the faint extrapolation test. So. So what we can see for classification is that the randomized test gives us very good results much quicker, and then oscillates within those good results, where the faint extrapolation test shows us a harder problem to solve and the longer training history actually. And then the case is reversed for the redshifts of quasars and galaxies, because the redshifts are much harder to solve in the feature space that we have with bound magnitudes. So here we can see that the training of the random validation set progresses longer, while the one on the faint extrapolation overfits quicker. Now, these training histories are already for models which are prepared to work well on both of those tests. If you use only the randomized test to tune your hyperparameters of your model, you will get this one blowing up much faster and problematic. So using such a faint extrapolation test allows us actually to see the whole problem of the learning of the model. And this is not that we simply prefer one line or the other. It's simply a trade-off that we have to be careful of. We have to know that it exists. And this is a comparison, other comparison, what this faint extrapolation test actually helps. And that's on the first rows, this is a comparison of a couple of different machine learning models. On the randomized test, what we get is that the extreme gradient boosting works the best for classification, while artificial neural networks works the best for redshifts. So one would probably say that it's the best to use XGB for classification and ANN for redshift. And that would be those results. But when we combine those models and use the faint extrapolation test, and the three last columns show the results not in the subset of true quasars, but in the subset of the photometric, what we call quasar candidates, basically, which comes from our model. And then it seems that the two models are working well, but they are in some disagreement with each other. And then this disagreement shows in this faint extrapolation test, which is harder, and actually shows that combining two different models gives worse results than using only artificial neural network. And we have also another example of how this test helps. Using different feature subsets in our work. So due to time limitation, I will now go to next things, but if I hope I managed to convince you to at some degree about that. The results, these are the results for classification on the randomized test and the extrapolation test. We get pretty good results on both of them. Which is due to the fact that we tune the hyperparameters of our model so that it's generalized well and also works for the faint data. for the redshift of quasars, this problem is in itself hard to solve. So we also get very good results on the randomized test, and definitely much larger scatter on faint data, but still very good results. And now final catalog. So testing of the final catalog. First, what we use is number counts. So we have a couple of different models here. Basically, the strain lines over here are the models from eBOSS, what we would expect to have. And now the whole catalog in the safe and extrapolation subsets is the green line. So you can see that soon after we reach the magnitudes higher than what we have in training, we get this Euclidean number counts. So these are probably mostly just stars that we have in the catalog. We do two different cuts. The last cut is at probability 0.98%, and that gives us this light blue line, which gives us proper number counts. But we also know that the kits is complete to about 23.5 from the plots that I had earlier. So probably here it's already the contamination. So that's the limit of this test. It tests completeness, but it doesn't test purity. But that's one cut that we have that we will skip. Another cut comes from parallax test from Gaia. So we have two different. One offset comes from the fact that Gaia has an inherent offset to all the observations, and then I calculate something which I call acceptable, which is based on the expected amount of stars in our catalog based on these numbers from the tests, and it also shows us a cut of about 0.9, but this is limited to magnitude much closer to training. So this cut 0.9 actually agrees with the cut from the number count 0.9, but limited at brighter magnitudes. It might probably be a bit quick and a lot what I'm saying right now, but basically these methods are in agreement, and they give us two different subsets of our catalog. One is safe catalog at limited at 22 and probability of 0.9, and this gives us this amount of quasars. Another one with includes extrapolation and but also higher probability cut, and gives us more than 300,000 quasars. And now we started with visualizations. Now we want to go back to visualizations and see how our catalog looks like. So on the left is the result of
1 minute.
our inference. Sorry, how much?
1 minute.
Okay, so that's almost the last slide. These are all our estimations. This has the training data, the ground truth, and on the right-hand side we can see that the phase extrapolation set actually is nicely close to the original group of quasars, but the points also lie in the space that we are not sure of. So maybe a bit more strict cut might be also needed here, but it's very nice visualization. So the catalog is ready for tomographic study of large-scale structure, which we want to do with cross correlation with CMB lensing and some more IG and astrophysical studies. Yeah, and this would be the last slide and main takeaway that I would like to repeat one more time. That's very important to understand data and also use some data research and visualization, and then test the model throughout, both on the stage of training the model with good validation approach, and then the final results of your model with some more physically driven methods. Thank you very much.
Thank you very much. Are there some questions? Frederick Corba.
Hi. Yeah, sorry, maybe it's me not following well enough, but on point 3, did you use Gaia parallaxes or will you use them? I mean, because in looking for strong lens quasars, for example, we use these to clean from blue stars and even pairs of blue stars, and it's super efficient.
Yes, so I used the parallaxes. This is the result of the parallax test. This shows the mean parallax, I think. Of this, the green line is our final catalog, and then there is a different cut at the classification probability when we decrease the size of the quasars. But the problem is that cross-match with Gaia was limited at R between 21 and 22, which is much brighter than kits. So that was the problem with this test. But we used it, yes.
Okay, thanks.
Any more questions? Sorry, and is there anything on Slack? Yeah, there's one. Okay, so The question is, have you checked what is the bias of your catalog with respect to X-ray IR detected quasars? As in, do you miss similar quasars as missed by SDSS, or do you miss something more or less?
I'm not sure if I understood the whole question. This is the analysis that we do on misclassification of quasars. So this is the training data, so cross-match with SDSS. So on top we have the true quasars and the result of our classification of true quasars, and on the bottom we have the objects that we consider as quasars, but they true labels. So we basically have mostly the misclassification comes from galaxies, but not just normal galaxies, but AGNs. And that's most probably due to the fact that in spectroscopy you have the slides that you can focus on the AGN, but in the broadband photometry, these galaxies are very similar to just normal galaxies, and simply the AGN inside is not that much visible. So that's the main misclassification. I'm not sure if that answers your question.
Okay, well, I guess you can discuss on Slack. And it's the end of the... There's one more question in the audience. Sorry. Just say your name.
Hi, this is Johannes Buchner. Quasars are an optional features of galaxies. Why do you divide galaxies from quasars?
So in our data, they differ a lot by their shape. So if they are point-like, they are very similar to stars, and the highest problem becomes how to classify stars and quasars. And then when you go to galaxies, this part between when we have galaxies with AGN inside or optical AGN might be hard for us to separate. This plot shows us the best that in the color space, the galaxies are actually quite far from what we call quasars, right? And they also lie on the very different redshift range, as we have the peak of quasars at redshift higher than 2, where galaxies are mostly present at redshift between 0 and 1. So they're actually quite different. It might be interesting also to see if we can model the transition part, but I think not from this data.
Okay, thanks. So one last question very quickly. Why t-SNE and not something else? That's from the Slack.
Yeah, I have experience with using many different things before I even started working in astrophysics, and just t-SNE always gave me the best results, and I like it the most. But there are of course advantages and disadvantages. But I think it allows for the most kind of flexibility. As for instance, sums are limited to the cells that you create, and I like this flexibility and the fact that it may show me some things that I may not even think of before. So I would recommend that.
Okay, thanks very much, and thanks all the speakers.